Hello everyone. This is the tutorial for chapter 9 and 10 by group 2. First, we'll start to Chomsky classification of grammar. In Chomsky classification of grammar, in grammar there are four different types of tuple. V for set of variables, T for set of terminals, P for set of production rules, and S for start variable. And in Chomsky classification of grammar, there are different types of grammar, which is type 0, type 1, type 2, and type 3. In grammar type, according to Noam Chomsky, again, there are different type of grammar, which is the type 0, 1, 2, and 3. And the table that I will show you will differ them from each other. In type 0, the grammar that it accepts is unrestricted grammar, and the language accepted is recursively enumerable language, and the automaton it used was the Turing machine. In type 1, there are context-sensitive grammar, context-sensitive language, and linear bounded automaton. In type 2, there are context-free grammar, context-free language, and push-down automaton. And lastly, in type 3, it is the regular grammar, regular language, and finite state automaton. In this illustration, it will show the scope of each type of grammar. So dito yung scope ng bawat type of grammars. In regular grammar, it is within the context-free grammar. And the context-free grammar is within the context-sensitive grammar. And the context-sensitive grammar is within the recursively enumerable grammar.
And the type 3 grammar is type 3 grammars generate regular language. Type 3 grammars must have a single non-terminal on the left-hand side and right-hand side consisting of a single terminal or single terminal followed by a single non-terminal. The production must be in form X rewrite A or X rewrite AY, where X, Y, and non-terminal and A. N T terminal, the rule S rewrite E is allowed if S does not appear on the right side of any rule. This is the example of type 3 grammar.
Type 2 grammar. Type 2 grammar generate context-free languages. The productions must be in the form A right to Y, where A epsilon n non-terminal and Y epsilon T U n square root of 2 string of terminals and non-terminals. These languages generated by these grammars are be recognized by a non-deterministic push-down automation. This is the example.
Okay, these are the type 1 grammars. Type 1 grammar is generated context-sensitive languages. The production must be in the form of alpha A beta goes to alpha lambda beta, where A is a subset of n or non-terminals, and alpha beta lambda is the subset of T union n asterisk. It's a string of terminals and non-terminals. The strings alpha and beta may be empty, but lambda must be non-empty. The rule S goes to epsilon is followed is followed if S does not appear on the right side of any rule. The languages generated by these grammars are recognized by a linear bounded automaton. And here are some examples of type 1 grammar. AB goes to A lowercase b, uppercase b, lowercase c. Uppercase A goes to lowercase b, c, uppercase A. And uppercase B goes to B.
In type 0 grammars generate recursively enumerable languages. The productions have no restrictions. There are any phase structure grammar, including all formal grammars. They generate the languages that are that are recognized by Turing machine. And the productions can be in the form of alpha goes to the beta, where alpha is a string of terminals and non-terminals with at least one non-terminal, and alpha cannot be null, and the beta is a string of terminals and non-terminals. And here are the example for type 0 grammar. S goes to AC, AB, and BC goes to AC and B. CB goes to the DB, and AD goes to DB.
Grammar. Grammar can be denoted by the capital G symbol and can be defined by a four-tuple. These are V, T, P, and S. V is the set of variables in a grammar. T is the set of terminals in a grammar. P is the production rules followed to generate the grammar language, and S is the starting variable. Okay. Regular grammar. Regular grammar can be divided into two types. There is right linear grammar and left linear grammar. Okay? Right linear grammar is a grammar that is said to be in the production form of A goes to X, capital B, A goes to X, where A and B uh, is the sum total of V, and X is the sum total of T. Whereas left linear is uh, is a production of the form A goes to X, B, A goes to X, where A and B is the subtotal of V, and X is the subtotal of T. Regular grammar. Regular grammar has these examples. These are S goes to A, B, S bar, B for right linear. S goes to S, B, E bar, B for left linear grammar.
So next is the regular expression. Regular expression can be recursively defined as follows. Epsilon is a regular expression, indicates the language containing an empty string. In here, like L epsilon is equals to epsilon for the containing language. And pi is a regular expression denoting an empty language, where L pi is equals to blank or empty languages. And another definition of regular expression. X is a regular expression where L is equals to X. The language is equals to X. If X is a regular expression denoting the language LX and Y is a regular expression denoting the language LY, then X plus Y is a regular expression corresponding to the language LX union to LY, where LX plus Y is equals to LX union LY. And X times Y is a regular expression corresponding to the language LX times LY, where LX times Y is equals to LX times LY. R is a regular expression corresponding to the language, where L is equals to R, or LR is equals to L, R. And in the fifth definition of regular expression, if we apply any of these rules several times from 1 to 5, they are regular expression. And here are the examples of regular expression. In here, if you see 0 plus 10 power, L is equals to, then the language or the language set is equals to 0, 1, 10, 100, and so on and so forth. If you look here on the second example, the 0 multiplied by the 10 power, then the regular set will be the regular set will be 1, 0, 1, 10, 0, 1, 10, and 0, 0, 1, 0, and so on and so forth. Then here there are different examples for a plus b to the power, set of strings of a's and b's of any length, including the null string. So L is equals to epsilon AB, AA, AB, BB, BA, and so on and so forth. And here, if you see the AA multiplied by BB, the set of string will be odd number. For example, B and the AAB, since it is multiplied to B, we start to B, then AAB, and so forth, so forth. And that's it for the regular expression examples.
Regular sets. Any set that represent the value of regular expression is called a regular set. Property 1. The union of regular set is regular. Let us take two regular expressions. RE1 equal to AA asterisk, and RE2 is equal to AA asterisk. So L1 A, and so on, string of odd length excluding null, and L2 is epsilon AA and so on, string of even length including null. Property number 2. Intersection of two regular set is regular. Prop. Let us take two regular expressions. RE1 is equal to A open and close parenthesis A, and RE2 equal to open and close parenthesis AA. So L1 is equal to A, and so on. String of all possible length excluding null. L2 is equal to epsilon AA, and so on. String of even length including none. L1 intersection L2 is equal to A, and so on. String of even length excluding none. RE open and close parenthesis L1 intersection L2 is equal to AA open and close parenthesis AA, which is a regular expression itself, hence proved. Property number 3. The complement of regular set is regular. Prop. Let us take a regular expression. RE is equal to open and close parenthesis AA. So L is equal to epsilon AA, and so on. String of even length including none. Complement of all of L is all the strings that is not in L. So L equal to A, strings of odd length excluding none. RE open and close parenthesis L equal to A open and close parenthesis AA, which is a regular expression itself, hence proved. Property number 4. The difference of two regular sets
is regular. Proof. Let us take two regular expressions. RE1 is equal to A, opening close parenthesis A, and RE2 is equal to opening close parenthesis AA. So L1 is equal to A, A. String of all possible lengths excluding null. L2 is equal to epsilon AA, and so on. String of even length excluding including null. L1, L2 is equal to A. String of all odd lengths excluding null. RE, opening close parenthesis L1 and L2 is equal to AA, which is a regular expression, hence proved. Property number 6. The closure of a regular set is regular. Proof. If L is equal to A, string of odd lengths excluding null. RE is opening close parenthesis L is equal to A, opening close parenthesis AA. L is equal to A, and so on. String of all lengths excluding null. RE is equal to A, hence proved. Property number 7. The concatenation of two regular sets is regular. Let RE1 is equal to opening close parenthesis 0 plus 1, 0, and RE2 is equal to 0, 1, opening close parenthesis 0 plus 1. Here, L1 is equal to 0, 0, 0, and so on. Set up a string ending in 0, and let L2 equal to 0, 1, 0, 1, 0, and so on. String of string beginning with 0. Then L1, L2 is equal to 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on. Set up string containing 0, 0, 1 as a substring which can be represented by an RE. Opening close parenthesis 0 plus 1, 0, 0, 1, opening close parenthesis 0 plus 1, hence proved.